Université Paris-Cité, laboratory map 5. He will talk today about the mean field framework and especially LLN and CLT results for diffusions on Erdős-Rényi graphs. Please, Eric.
Okay, thank you very much. Thank you for the invitation. I will talk about interacting particle system and the large population behavior for mean field interacting particle system. I will not suppose any prior knowledge about mean field dynamics. The first part of my talk will be to recall what's known about these quite old results. But anyway, don't hesitate to interrupt me if there is anything not clear. And the point of my talk is to analyze perturbation of this mean field framework. So this is a joint work with Sylvain Delattre and Jean-Baptiste Giacomin, and also with Fabio Coppini and Christophe Poquet in the second part. So basically, what we are interested in is so usual mean field dynamics. What I want to look at is the following. So you look at capital N interacting diffusions. So xi of t is in Rd. So N is the size of the population, and think of N to be quite large. We will soon make N goes to infinity in a moment. And the basic framework for mean field dynamics is to consider the following type of SDEs. So we have a system of coupled SDEs, which can be decomposed into three parts. The first part being some local dynamics, and plus some interaction between along all the population. So you have coupling, a binary kernel between two particles, so gamma of xi and xj. And the principle of the mean field approximation is to sum over all the population. So you have 1 over n, the sum of all j of this binary kernel. And you're doing probability, so let's put some noise as ID Brownian motion. And the standard framework is to suppose that the initial condition is some ID random variable on RD. So this is quite an old subject because it goes back to Cax and McKean. There is also a nice law course by Slitman. And originally, people were interested in Boltzmann equation and Hart-sphere collisions. More recently, only to cite a few subjects I'm interested in, there are plenty of applications of this kind of dynamics, but only to cite neuroscience. So you look at interaction between neurons. You have plenty neurons in the brain, so it's quite obvious to take n goes to infinity in this kind of framework. So there are plenty of models such as Hodgkin-Huxley, Fitsu-Nagumo, where the variable xi is mostly the voltage of a neuron. So you are interested in the way neurons are interacting with each other. Also application in the statistical physics. So you may think of Curie-Weiss or XY or oscillators model, which can be also approximated by this mean field dynamic. I have defined this as a solution of interacting diffusions, but you may also think of dynamics with jumps. So you may think of Hawkes processes, integrated fire, PDMPs. So there are many frameworks where you have this kind of interaction. But I will stick to diffusion because it's simple and you can already do something on this kind of thing. Okay, so this is the mean field framework. And the point is that we have all-to-all interaction. So everyone is talking to everyone. Okay, for simplicity, I will just suppose that this F here is 0. So you have no local dynamics. And I will also suppose that this is one in this framework. This is only some notational purpose, but it's really not really important to suppose that you have F is 0 here. And the point of this mean field approximation is that everything is functional of the empirical measure of the system. So you put a Dirac mass at each value of the process, and you take the mean value of this. So this is the empirical measure. So this is the probability measure for each n and t, and it's a random process with respect to this, with value in this set of probability measure, because you have randomness coming from this xj, and also this depends on t. So you have this is a random process. And of course, if you look at this quantity, everything can be written in terms of this empirical measure here. So basically, the intuition is that once you know the empirical measure of the system, you know everything about the dynamics. Okay, so what's the limit? What can we say about the limit of large population? So you want to make n goes to infinity in this kind of framework. So the intuition is quite easy. Of course, these are not ID random variables, so you cannot apply your standard law of large number for this kind of empirical measure. But you can imagine what should be the limit for this kind of model. So suppose that you are allowed to take n goes to infinity in this kind of thing. The only possible limit for this kind of model is to define this system. So you have x bar, where this mu n goes to some mu t, deterministic. But once mu n is also the empirical measure of the system, mu t should be itself the law of the process x bar. So this is what we call the nonlinear process associated to this system. Is nonlinear because x bar depends on mu t, but mu t is also the law of x bar. So x bar interacts with its own law. And in particular, it's not quite clear that this system is well posed, but it does. So this is quite under standard assumption of gamma and suitable moment condition on the initial condition. It's quite easy to see that you indeed have some. This system is quite well posed. This is only by a fixed point formulation for this kind of system. So there is a unique pathwise solution to this nonlinear equation. And what we call propagation of chaos for this kind of model is to see that you can indeed couple the empirical system, so the microscopic system, with ID copies of this nonlinear process in such a way that the difference between the microscopic system and its limit should decrease as the square root of n as n goes to infinity. So the coupling is quite easy. You just take the same initial condition, and you also take the same noise for each I. And actually, the proof of this inequality is quite easy to see. So let me just give you some flavor of the proof. Okay, why is it working? Okay, sorry. So intuition of the proof is quite easy. So you want to relate the particle system, which interacts through the empirical measure of the system, with its limit. So once again, you take the same Brownian motions, you take the same initial condition, and you want to take the difference between the two. So, of course, since you have the same Brownian motion, this disappears, initial condition disappears. So everything boils down to estimating the difference of the interaction kernel. So you have this difference here. And the point is to introduce the empirical measure of the limit of the x bar j, which is nothing else than the empirical measure of ID nonlinear processes, because you have ID Brownian motion here. So if you take the difference here, well, you have three terms. The first two terms, for example, the first one is only a comparison between xi and xi bar. So this will only give you gradual terms in the estimation. The second one is also the same because you are comparing the empirical measure with its mu n bar. So these two will give you gradual terms. And the third one, is nothing else than the comparison between the empirical measure of ID particles with its limit. So the third one is only a variance term. So this is only some the law of large numbers, the standard law of large number will give you the convergence of this guy to 0 as n goes to infinity. So this is this term that gives you the 1 over square root of n, which appears here. So this is quite an easy argument here. So it goes back to Bakins, Nisman, and many others. Okay, so once you have compared the particle system with its limit, you still can say something about the empirical measure. So for the bounded Lipschitz distance defined as follows, you have immediately the fact that you also have the convergence of the empirical measure to this mu t. And this mu t, from a PD perspective, it solves the nonlinear Fokker Planck equation, which is written here. So here you have the term, the Laplacian term coming from the noise. And here you have the interaction, nonlinear interaction term coming from this binary kernel here. Okay, so this is the quick recall about what is known about mean field asymptotics. So this is the law of large number part of my talk. You may also want to be interested in the fluctuation results. So basically, you have this empirical measure which goes to mu t. You want to renormalize things and multiply by square root of n and study fluctuation around this. What is the status of this process? Well, this is the difference between two probability measures. So it's a side measure. So the best way to see that is to see it as a distribution. So you apply it to test function, regular test function, and you want to look at the limit of this quantity. An approach which has been followed especially by Fernandez and Melea in 1997, it was to write the semi-martingale decomposition of this eta m. So you apply it to a formula and you have this kind of dynamics. Here, this is the initial condition. Here, you have a second order linear operator which captures the interaction in the system, and you have some noise which basically goes to some Gaussian noise as n goes to infinity. And the point of the work by Fernandez and Melea was precisely to show that you can indeed make n goes to infinity in this equation. And what you end up at the limit is that you have a linear SPMES solved by this eta t, where WT is some Gaussian noise for this process. So this is what we know about mean field dynamics. We have this law of large number, and we have these fluctuation results concerning the empirical version. Okay, so now what I want to consider is perturbation of this kind of dynamics. Cool. So let me just recall the system. One crucial assumption concerning this system is that you have all-to-all interaction. So basically, each particle is talking to everyone. So the graph of interaction is the complete graph. And interaction are homogeneous in the sense that the strength of interaction is the same order, 1 over n, over all the population. And these two assumptions also allows for exchangeability for this kind of system, in the sense that if you assume at t equal to 0 that you have, for example, ID initial condition, at any t, the law of the vector x1, xn is invariant by permutation. And this is quite nice because you have, once you have this property, you have every kind of convergence results concerning exchangeable process, which allows for many proofs and many. Okay, so you have this property which is quite easy for many applications. Okay, but my point is that from the modeling perspective, this suffers from several limitations. If you think, for example, of neuroscience, so neurons within the brain, it's quite obvious that the graph of interaction is not complete. So in your brain, each neuron is not talking to everyone. So, okay, from what I understood, biologists do not really know the graph of interaction within the brain. But the point is that, however, mean field approximation are quite commonly used in this kind of for this kind of dynamics. So the point was to understand this kind of paradox where, okay, many people use mean field approximation, whereas the actual graph of interaction is not the complete graph. And one thing also which is important is that you may not want the initial condition to be independent and identically distributed. What we really want to have is that only that the initial empirical measure converge. So what we have been looking was this kind of perturbation of mean dynamics. So now you give yourself a graph. So with vertices 1, n. So at each vertex you have this particle xi. And now what you have a non-trivial graph of interaction in the sense that for every edge I to j that you have in your graph, you have this epsilon ij, which is 1 if this edge is present, and 0 if there is no edge in your graph. So now how do you modify the dynamics? Well, you only sum over all existing edges within your graph. So you have this 1 or 0 depending on the presence of your graph, plus noise. Okay, you have still this binary interaction within your graph. One thing which is important is that you no longer need to renormalize by n, because your graph may be diluted and the correct renormalization should not be n. So what here you have to renormalize by the exact degree of each vertex, so that as n goes to infinity, this term should remain of order 1. Okay, so now I have this interacting particle system interacting on a graph. And the question is quite simple. Does this model, is this model close to the mean field model? So the question is, how large is the mean field universality class? For which class of graph do you expect the same behavior as n goes to infinity as for the mean field dynamics? This is quite intuitive in the sense that if you start with the complete graph, but you remove only one edge, for example, the edge between 1 and 2, of course, as n goes to infinity, the fact that you have removed this edge won't change anything to the large population behavior. So you still expect the same mean field asymptotics if you remove sufficiently few edges. But you want to make this precise, and you want to make this precise at both levels, so at the level of lower Flash number, but also at the level of fluctuations. One point here which is crucial here is that since you have this non-trivial graph of interaction, your system is never exchangeable. Even so, you suppose that you have exchangeability at t equal to 0, you lose the exchangeability of the system. Okay, so just let me talk about the law of large number. So, okay, a simplifying hypothesis for this talk will be to assume that Gn is an Erdős-Rényi graph. So, for now, I will suppose that each edge is taken independently with some Bernoulli law with parameter Pn. So, Pn is the probability that an edge is present in your graph, and you do the same for all edges independently. Okay, so in that Erdős-Rényi graph, the degree of vertex is binomial, npn. So approximately, in average, this is npn, the degree is npn. So it's not very difficult to show that the system should be the same when you renormalize by the exact degree or by the expected degree. So for now, we only renormalize by npn. And actually, you are interested in two kinds of regimes. First regime where Pn, so the dense case, so when Pn is constant. So in this regime, the degree of each vertex remains of order 1. So think of P because is 1/2, for example. You just remove half of the edges in your graph, but still you have something which is proportional to n. But you may also think of the case where Pn goes to 0. So, which is what we call the diluted case. So, as n goes to infinity, you have fewer and fewer connections in the graph. So, the degree of each vertex is now smaller than n. Okay, so let me talk about the law of large number. Why is it difficult? Actually, the difficulty is already present if you only remove one edge from the complete graph. Why is it difficult? Because now the interaction is no longer a functional of the empirical measure. When you look at this interaction, this is actually a functional of a local empirical measure. So you are only summing over all neighbors of the vertex I here. So you sum over all j, such that this epsilon ij is 1. So you are summing over all neighbors of I. So you have a collection of local empirical measures. And absolutely nothing tells you that this local empirical measure should be the same for all the vertex, and that this local empirical measure should be the same as the global empirical measure of the system. And okay, so the difficulty comes from the fact that you no longer have a closed formula for this empirical measure. If you compute Ito formula for this local empirical measure, you see that this local empirical measure will itself depend on a higher order empirical measure, which encodes for local motifs in your graph. So there is no closed formula for this kind of family. And this is the difficulty of this kind of analysis. Okay, but anyway, at least at the law of large number, there has been some collection of results. So the result is the following. So the fact is that this mean field limit is universal once you suppose the following. So you suppose that the initial empirical measure converges to something. So you need not suppose that your initial condition is ID, only that the local empirical measure converges to something. And then for almost every realization of your graph, so this is a quench result, as long as npn goes to infinity, you still have the convergence of the empirical measures to ut. So this is quite the optimal result in a sense, but this has been proven under various assumptions. So the first one, with Sylvain Delattre and Giambattista Giacomin, was to prove this kind of result under ID assumption on the initial condition, and something which is a dilution condition, which is quite weaker than this one. And there is also this paper with Fabio from Fabio Coppini, and Giacomin, who proven also who removed this ID assumption on the initial condition. And also this paper where we have proven this kind of result under the optimal condition. Why is it optimal? NPN goes to infinity. So NPN is the average degree of one vertex. So you need that this NPN goes to infinity. This is optimal because when you look at the case where NPN goes to some lambda, well, it's quite known that in this case, the Erdős-Rényi graph converges locally to some Galton-Watson tree. So you no longer have the same mean-field dynamics for this kind of system. And this concerns empirical measure, but you also have the same kind of dynamics for the local empirical measures that I defined earlier. Okay, so in a way, the mean field dynamics is universal as long as you suppose that each vertex is interacting with a diverging number of neighbors. Okay, so this is for the law of large number. What now about fluctuations? Okay, so we still have the same problem in the sense that if you want to write semi-particle decomposition of my fluctuation process, I can do that. So I can write Ito formula for this process. The problem is that you have supplementary terms coming from this Ito decomposition. And especially, you have the emergence of auxiliary fluctuation process, which are written here. So this at eta n is something which acts on the particles with two variables, on test function with two variables. And we see that it encodes for the proximity of the graph with respect to the complete graph. So here, this should be epsilon, sorry. In the case where we would be interacting on the complete graph, this would be 1, Pn would be 1, so this would be 0. But since we are interacting on the non-trivial particle graph, we have this quantity. Okay, but how do you prove that this auxiliary process goes to 0? This is actually not easy because okay, a strategy would be to write also a semi-particle decomposition for this auxiliary process. But still, you see that you cannot close the decomposition because this at eta n will also itself depend on higher quantities which encode for the presence of edges and motifs in the graph. So you want to find a way to close this decomposition. Okay, so let me just give you the result. Actually, the good news is that this term Cn is already small. So we can prove that this Cn goes to 0. So the fluctuation of the local empirical measure is only captured by this decomposition for the two. So you need to have this fluctuation process, but also this auxiliary fluctuation process. So the results are the following. You suppose that initially the initial fluctuation converge. You also have this dilution condition, which is quite weaker than the one for the law of large number, but still tell something about how small this Pn should be. And then for almost every realization of the graph, eta n at eta n converge to a system of coupled stochastic partial differential equation. So what is the difference between the mean field fluctuations? The mean field fluctuation corresponds to the case where this auxiliary process is zero. Because if you suppose that this is zero, this vanishes and you retrieve the usual fluctuation process of Bernoulli and Melia. So the question was to understand in which case do we have that this auxiliary process is zero. This is zero if you choose the initial condition independently on the graph. So, for example, if you suppose that the initial condition is it does not depend on the graph, then under the previous assumption, the fluctuations are the same as the mean field case. So this auxiliary process is zero, and you retrieve the usual mean field SPD. So in this sense, the fluctuations are also universal, provided that you choose the initial condition independently on the graph. But let me just stress that this result is also valid for initial conditions that may depend on the graph. You only suppose that the initial fluctuation converges. And we have also built with Fabio and Christophe a case where for well-prepared initial conditions, so that depend on the graph, the fluctuations are not universal. So they are fully given by the system couples of eta and at eta, but not only eta. So if you choose carefully the initial condition that depend on the graph, you end up with fluctuations that differs from the mean field dynamics. Okay. So just how much time do I have left? Maybe 10 minutes. I just want to give you some idea of proof for this kind of things. So basically, the point is to estimate auxiliary process, fluctuation process for this kind of quantity. So once again, this empirical measure, higher order empirical measure, captures the proximity of your graph with the complete graph. So you are comparing epsilon ij over Pn to 1. So this should be small. This is actually small if you take f, if you remove this f. So if you take f equal to 1, you are just summing independent and identically distributed variables. So you have every concentration result that you want for this kind of quantity. But of course, the problem is that you have this f here, and this f is very annoying because in this f you have xi, xj, xk, which depends in a highly non-trivial way on the graph. So the decorrelation that you have for this kind of variable is absolutely no longer valid for this with this quantity. So you need to find a way to decouple these two terms. And the key idea is the use of Grothendieck inequalities. So this Grothendieck inequality goes back to what have been used for purpose of functional analysis, also for computer science. But the main thing is the following. Grothendieck inequality is mostly saying that if you are looking at sums, so you're really looking at this kind of sums here, the point is to be able to write these sums in terms of scalar products in some Hilbert space. But once you have this quantity, and in this quantity you may have very difficult dependence between this scalar product and this AJK, But how do you decouple this in the sense that this quantity is bounded by the same quantity, but when you have replaced this non-trivial scalar product by signs. So in the worst case, once you know how to prove concentration results about this quantity where we have the supremum over all possible signs, you can control something like this quantity. So the point is to apply concentration results on this quantity and then to proceed with the similar estimates on this kind of things. Of course, the price you have to pay in doing that is that you lose control mostly on the dilution condition that you have to pay a price because you are looking at the worst case for this kind of quantity. So this is why, for example, in our proof we only have this weak dilution condition for this graph. Okay, so what's the point? The point was to prove that even you observe some mean field dynamics. I don't know if at the level of frame. This is not because you have already made microscopically a complete graph of interaction, but actually the mean field limit is quite universal, assuming that you have a diverging degree for each vertex. You may also, I only talked about homogeneous Erdős graph, but you can generalize this kind of results for inhomogeneous connection. So you may, for example, suppose that you choose your connection still independently, but inhomogeneously. So you no longer have an homogeneous Pn along the graph, but you may choose with some kind of function W, okay. And at the level of CLT, you still have some universality, but this universality is only valid as long as you choose the initial condition independent of the graph. Okay, so the fact that this dilution condition may not be optimal is not clear, but this is due to the diffuse of quantum inequalities, maybe with other ideas which should improve this, but I have no proof for this kind of things. Okay, so I think this is quite done. So I thank you for your attention. If you have any questions.
Okay, thank you very much, Eric. Okay, so is there any question in the room at IMPA? Yes, so there is Hubert who has a question, and also in the Zoom room. Please tell me. So Hubert.
Hi, Eric. Thank you for the nice talk. I wanted to ask you about your last slide. Okay, I don't know what W random graphs are, but so for instance, if you just take a graph which is not random, but for which and which is transitive and for which the degree is high. So for instance, take the circle and connection up to a distance that grows with n. Do you get this result or?
Yeah, well, at least for the law of large numbers, this is true. So you still have this, where am I? Sorry, here you still have this kind of estimate as long as you know you can estimate the proximity of your deterministic graph with respect to the complete graph. So this proximity is expressed in terms of some kind of distance which I've not defined here, but basically what you want to compare is you take a portion of your graph and you look at the density at some point, at some portion of your graph, and you compare it with the constant density of the complete graph. and you take it uniformly along the graph. So you have some kind of distance. And once you know that this distance converges to 0, you still have this convergence. So this is not only true, but for the Erdős-Penny graph, but you have many graphs for which this is true. The crucial point is that you need that in average. So I don't know what that means for a deterministic graph, but in average, the number of neighbors for each vertex goes to infinity.
Okay, so you don't need to be especially you don't need
random.
your graph to have a small diameter. For instance. No. Okay, thanks.
Okay, another question in the room is Claudio. No question in the room. No. Now on Zoom. I don't see. Yes.
So about this NPN to the fourth condition.
Yes.
So it's somehow related to the fact that you see you start to see more of this many body interactions when you try to improve this condition, that you have to also take care of also it's a 3-body interaction, 4-body, 5-body, etc. Or it's not related to that at all.
Okay, so I don't have a clear view about it, but one condition that I should have expected would be n to the square goes to infinity. Because npn to the square, you basically saying that pn compares to 1 of the square root of n. So for this kind of regime, you expect to see also the fluctuation of the graph itself, competing on the same scale with the graph, the fluctuation of the dynamics. So here you are saying that you are far from this regime. So this is okay. I would say that the optimal condition would be npn squared. And I would expect different kind of behavior for under this regime. But this limitation here is mostly due to the fact that this is the best that we could do with respect to this kind of Grothendieck inequalities and concentration results for this kind of worst case scenario for this kind of statistics. Because okay, the price that you have to pay here is that okay, you have non-trivial dependence with this kind of f here with respect to your graph. You want to get rid of that. The price you have to pay is that you have to study the worst case, the worst possibility. That is the supremum of all possible signs in this kind of thing. But this is quite strong. You may think that if you are able to improve this kind of inequality, you may suppose that you may improve this kind of condition. But maybe another point is that there is, well, I've been quite convinced that there is no real possibility of improving this kind of dilution condition in adding some other auxiliary process for this kind of dynamics, because if you continue this decomposition, so you may look at the dynamics of the CNT, which essentially is this one. So you once again apply two formula to this guy. So you have higher order statistics for this kind. The Grothendieck inequalities are getting worse. The estimates that you have for this kind of statistics are at some point you saturate. I mean, okay, we have not being able to improve the speed of convergence and this dilution condition in improving the order of the statistics. But okay, maybe we have missed a point here, but for now, I do not have any clue about how improving this dilution condition.
Okay. So I think there is no question on Zoom. So in the room at Timpa, there is another question, or cannot see. Don't think so. Yes. No. Okay. So if there is no question anymore, then thank you very much, Eric.
Thank you.
Have a nice time in Paris, and
Yeah, you too.
a nice time in Brazil too. Goodbye.
Okay, see you.
Bye bye. Merci Eric.